Hi, my name is Brian McVay, and my partner Todd Keiser and I are doing a demonstration of Faraday's law. We're dropping 9 3/16 inch rare earth magnets through solenoids of various numbers of turns. Right now we have a solenoid wrapped around the body of a ballpoint pen. We have 800 turns of wire on there, and we are hooked up through these leads over to this oscilloscope. We're using that to record the amount of voltage that is output from the coil after the magnet passes through.
Okay, so we're about to drop the magnets from a height of 9 inches, and with this video we're going to be watching the screen of the oscilloscope, so you guys will be able to see what happens here. Alright, you ready, Brian?
Yep.
Okay, so I just saved that on the screen, and it's kind of hard to see because it's a little fuzzy at the top there, but each there we go, hit the lights. Each increment on the screen there, each large square, is 500 millivolts. So right here we're right at about a volt there, you can see with the first sinusoidal wave. Okay, so here we are again, only we've changed out the coil. We now have 400 turns instead of 800 turns, and we're again going to be dropping from a height of 9 inches, and so we'll be able to see the resulting voltage on the oscilloscope here. Ready, Brian?
Yep.
Okay, so here's our saved result here, and as you can see we're pretty close to, let's say, 2.5 increments there. So each increment's 200 millivolts, so we're right at about half a volt there.
Okay, so as you can see in our little vise here, we have our solenoid of 200 turns, again around the body of a ballpoint pen. We're going to do another drop from 9 inches and hopefully get half of the voltage that we got from the 400 turn solenoid, and hopefully a quarter of the voltage we got from the 800 turn solenoid.
What were those voltages?
In the 400 turn solenoid we had a voltage of 480 millivolts. In the 800 turn solenoid we had a voltage of 1 volt. So hopefully this should come out to be around a quarter of a volt.
Okay. So you're at 9 inches there?
I'm at 9 inches there. You want to set the oscilloscope.
Alright, here's our screen. You ready?
Ready when you are.
Go. Alright, he's going to hit the lights. Alright, we're at an increment of 100 millivolts, so it looks about 2.5 increments there. So we're right at a quarter volt, just like Brian predicted.
Alright, so now that we're done in the lab, it's time to go to the computer and see what kind of data we were coming up with. So as you can see here, we dropped from 4 different heights, 3, 6, 9, and 12 inches, for 3 different coils, 800, 400, and 200 turns. So you can see that voltage increases proportionally with the height and therefore the speed that the magnets were traveling at when they traveled through the solenoid. And then voltage also increases proportionally with the number of turns around the solenoid. So I just want to show you a graph here that encompasses everything. This is voltage induced versus height dropped. The top line there is 800 turns, middle is 400, and the bottom is the coil with 200 turns. And you can see here that the voltage induced is proportional to the speed that the magnets were traveling through the coil. And then you can also see that the coil with 800 turns is 4 times greater than the coil with 200 turns and 2 times greater than the coil with 400 turns.
Okay, so straight out of Dr. Buckner's notes, we have a definition of Faraday's law of induction, which states that time-varying flux linkage induces voltage in conductors. So that's exactly what we saw today experimentally. And then right across the page is Faraday's law in equation form, which states that the voltage induced equals negative d lambda dt, or the change in flux linkage per unit time. And then right below that, flux linkage is directly proportional to N, or the number of turns in the coil. So I hope you guys were able to see that Faraday's law both experimentally and also mathematically here and on the computer. And just want to say a big thank you on behalf of Brian and I to Dr. Buckner for giving us a fun project to work on. Thanks.